This video is going to cover multi-trait multi-method models. So I highly recommend the Brown Chapter 6, but also Dave Kenny's website that covers some pictures on how these look and some of the issues and concerns with those particular types of models. So a multi-trait multi-method model really allows you to look at convergent and divergent validity, and so it's kind of like a double CFA. So you're going to have the CFA side for the traits. This is the normal thing we do. And those are the factors that you're trying to measure. But you're also going to have a CFA side for the methods. And it's the way we're trying to measure it. This applies a lot in IO and clinical fields where you have multiple scales that measure the same thing. And you're trying to see if they are convergent in their measurements and divergent in their trait measurements as well as individual measurements, because if you have two scales that measure the exact same thing, why are you using both of them? Okay. So the biggest thing is really convergent validity. So how much do those different assessments measure the same trait? And you want them, if they say they measure the same thing, to measure the same thing. So I want scale 1 and scale 2 to measure traits equally well. Now that doesn't mean that they're measuring the exact same variance equally well. So let's say you have two scales for depressions. Two of the most popular two are the Beck Depression Inventory and the CESD. People keep using them, both of them sometimes, because they measure depression well, but they measure different aspects. And so that's what we're really looking for, is hopefully, in a perfect world, scales that measure our traits well, but are divergent in their measurements. And so that's going to be discriminant validity. So how much do the different methods separate their measurements? So I want scale 1 and scale 2 to measure those traits slightly differently, which means that both scales are going to be equal. So they measure the trait well, but differently, so that I can use both of them to gather more information about someone rather than less. If they measure the exact same variance in the exact same way, then only use one of the scales, because otherwise you're wasting your time and the participant's time if you're using both. Alright. Another thing we can look at is what's called method effects. So how much those scales overlap in their traits. So I want my scale, individual scale, to measure those traits differently. That effect essentially says that the traits are different things because they're different things and not because of the scale that we're using. So it should show some discrimination between traits as well. So there should be discrimination between methods and between traits, but converge on the fact that these traits are being measured in the same way. So you kind of have to you get to do both, and we're going to talk through about the procedure that you can use to get all of that information. Okay. So with model comparison, this is basically a set of nested CFAs. These are definitely nested. We're just changing the paths, coefficients, or deleting paths. So we can use that chi-square difference test. That's probably the most popular. You could use AIC and ECVI, but it might be a little too sensitive because there aren't really cutoff rules for those, but definitely chi-square is the most common used in this example. Or we can use our rule that we're going to talk about a lot for multi-group models, which is a change in CFI. And that would be a 0.01 is a significant change in fit. So when we get to examples for MTMM, we'll try both, chi-square difference test and the CFI, to see if they agree, because sometimes they don't. Okay. So there are a lot of approaches to MTMM. Some of them just have to do with looking at correlation tables, but we're going to cover very specifically the Widaman rules and correlated uniqueness. And it's two separate approaches that kind of have some similarities in the way that you analyze the data, but you would either do the Widaman steps. They're slowly losing favor because the models tend to have difficulty converging on a reasonable solution, or correlated uniqueness. You wouldn't do both. Okay. There are lots of different ways, though. If you Google MTMM, you will find lots of options. So the first thing you want to do is make sure you understand model specification. This is more specific to Widaman, but this is not a normal CFA. We're really interested in the loadings of the paths, so we don't want to do the marker variable scaling. Instead, we really want to focus on variance scaling. So we want to set the latent variables to the scaling factor so we can look at the probabilities of each loading as well as the strengths of the loadings. So in this particular type of analysis, the strengths of those loadings is more important than before. So now we're going to standardize on the latent variable. So the first model we're going to program, there's going to be 4 in the Widaman rules, is it's called correlated traits, correlated methods. So you're going to correlate the traits on one side of the model, correlate the methods on the other side of the model, but do not cross-correlate methods and traits. So just a quick Widaman note, you will have to turn off those cross-correlations. And so what you would do is method latent, tilde, tilde, trait latent, and put a 0 in there so that you're forcing those particular paths to be 0. Now the sim plot picture that you'll get from these are really ugly, so I have some examples from a nicer drawing one. So this is your correlated traits and correlated methods model. It didn't totally copy from the internet that great, but you'll get the idea. So over here they have methods, 2 different ways to measure this particular whatever it is. Oops. And then over here we have traits, and these are the 4 different traits they're measuring. Although, in a sense, this isn't necessarily the best type of model because each factor only has 2 indicators. So with methods over here, each method is linked to its item, and so there are 4 on each one, and then each trait over here is linked to its trait. So they should, each square here should have 2 different arrows, one for methods and one for traits. So you can't have a trait that's only on one of the methods. So the traits have to be on both methods, and then the methods have to measure all the different traits. So that's correlated methods, correlated traits. You want this model to be good. So this is sort of the golden model, which is what's on this side. So one of the biggest concerns and sort of complaints about this set of procedures is that this is the model that's likely to blow up. So you might have a Haywood case here and a negative error variance, because look at what's going on. I've got the method predicting it and the traits predicting it, and sometimes it just cannot figure out what error variance should go here on the item itself, and it's likely to throw an error. And that's mostly because the models are fairly complex, and a lot of the stuff is correlated sort of on purpose. Obviously, items are going to be strongly related to their traits, you hope, and their methods, so sometimes it just gets kind of confused in a sense of where those correlations should go. Not literally because this is math, but that's the idea. So what happens if you do get a Haywood case? Since all of the error terms are on manifest variables, so they're all on squares here, what I've always done is calculated the variance for that particular item and used that to set the value to something small and positive, because we are setting variances here, and so it would allow me to set that variance to something kind of small. And if you know the variance by having that data, you can set it to that, or you can set it equal to another small positive parameter. So if all of them are 0.05, you can set it to something very close to that, and just sort of force the model to say, this is the variance, move on from there. And that'll often fix it. Now, with the step-down comparisons, like I said, Model 1 is the best case scenario, where the traits are correlated but not perfectly, because that implies the traits would be the exact same, and then the methods are correlated but not perfectly, because then that would say that the methods are the same. And then the items are estimated best by the measurements. The items are best measured. One more time. The items are best measured by traits, so they're linked mostly to the psychological phenomenon that you're trying to measure, and they're estimated by the measurement they're on, because naturally that happens, but not perfectly. Okay, If you got none of that, that's okay, because we're going to walk through each one of these comparisons and talk about how they work. So with model 2, we're going to delete the traits. So it is a no traits correlated methods model, and we're just taking out the trait latents. So leave the indicators alone. The methods, the methods stay in there. So we're just testing methods at this point. So it kind of looks like this. This is the original model. This is the new model. So we're just kind of deleting this side. As I'm saying, leave the indicators in. So when you're cutting and pasting the lines out, don't take these out wherever you define them. So with Widaman, it's easy. You just take out the lines that are specific to the methods. You also have to take out the cross correlations setting to 0 because it won't know what to do because these don't exist anymore over here. And so this model should be worse because we've taken out the traits. At this point, we would say if this model was the best, that it was all measured by methods, which is not good. That implies that there are no traits, that everything is a method effect, which is bad. So this would be convergent validity. So it's independent measures of the same trait are correlated, which is model 1. And so we want model 2 to be worse than model 1. So model 1, here's a kind of like way this works. Model 1 has both the traits and the methods. Model 2 only has methods. If model 2 is good, that means the methods are the best estimate for the data and that the traits are not useful. And that's bad. You really want your traits to be the real reason that you get the output you get, not the scale. Okay, so that's the best way I think about this comparison, 1 versus 2, is that I want my traits to be important enough that those scales don't matter. And if the model with only the scales is better, that implies these traits are not useful. Model 3, compared to model 1. Okay, so we're comparing everything to model 1. That's going to be different from when we talk about multi-group models where things are compared in successive order. So this is, everything is still compared to model 1. We've got perfectly correlated traits and freely correlated methods. So we're going to have traits and methods both sides again, but we're going to set those double-headed covariance arrows to 1 on the traits side. Okay. And this implies that the traits are all the same. So I kind of try to draw this on here where we would add these correlations and set them all to 1. That implies that this is not a 4-factor model, it's one giant trait altogether. And so this is a discriminant validity test of the traits. So I want my traits to measure different things, and so I want this particular model to be bad. If we're comparing our model 1, our freely estimated model, to model 3, and they're exactly the same, that implies that the traits are so correlated that they're not distinct things. So this is a discriminant validity of our traits question. So we want these two models to be different and model 3 to be worse. Now this is a weird step. Model 4 is freely correlated traits and uncorrelated methods. So we're going to set the covariance between methods to 0. Okay, so we're going to set this side to 0. And what that implies is that the methods are distinct animals, so that they are different things. And if our methods correlation is above 0, that implies they're measuring the exact same variance, and that means why use both of them. Okay. So with model 1 versus model 4, we actually don't want them to be different. Okay, so this is a discriminant validity test. We want our methods to be measuring different pieces of variance. Otherwise, why would we use them all? So we're trying to say they're distinct methods. There's a purpose to having multiple scales. So we want to freely estimate the correlations, from model 1 to be equal to the 0 correlation in model 4. So effectively, this is a test of if the null hypothesis, right? If R between these two, the correlation, is 0. And we want it to be 0. Or something close to 0. So this allows for some variance, but we want it to be a small correlation, and this will tell us if that is effectively 0, which would be good, because that means that the methods measure different things. I can't always get this particular step to work, because often methods measuring the same traits have higher correlations than 0. It isn't too surprising that this doesn't always work, but in a perfect world, they would be different enough that we would get correlations between methods to be 0. Lots of M words in this lecture. So after you've done those 3 comparisons with the model that's best, which is hopefully model 1. So for this section, it doesn't say this on the slide, but it should. For the parameter estimates, looking at those, you go back to model 1. And you create yourself a table. So for each item, we want to put the standardized loading for traits and methods. I kind of made this table up a little bit to keep it kind of simple, but let's say item 1 loaded on this trait and this method. So I put an X in things where I didn't need a number. So it won't have all 4. It'll have 1 for traits and 1 for methods. Okay. And then if I filled in those numbers with some fake data here, essentially what I'm wanting to find is that the trait loadings, the standardized loadings, are higher than the methods loadings. Okay, these are standardized because we're standardizing on the latent variable. Okay. So these will be z-scored. And this finding will tell you that the trait effect is better than the method effect. Okay, that's not something we've tested so far. So far we've said the methods measure the traits in the same way, but they measure them, different pieces of those traits in the same way. So that's discriminant validity of the methods, convergent validity of the traits, and then we also did discriminant validity of the traits, meaning that the traits are not perfectly equal. Okay. What we haven't said is that the trait effects are bigger than the method effects. We've said that the methods, hopefully, having those traits are important, but what if they were equally important? That's still not good. So we want to say that the reason that we get the answers on these scales, or whatever they are, is because of traits way more than methods. This is the way to look. Okay. So what you do is you want the trait effects over here to be larger than the method effects over here. So 0.89 is a lot bigger than 0.24. Unfortunately, there are no hard and fast rules for this. In a perfect world, actually the loadings on the traits would be very close to 0 because everything was methods. Oh, I said that backwards. Wait, the loadings on the traits would be very high. The loadings on the methods would be very close to 0, meaning everything is traits. Sorry, this T over here confused me. And I'm a squirrel. So we've got trait effects over here are very large. Method effects over here are very small. So 0.89 bigger than 0.24, bigger, bigger. And on one of these I flipped them. So in this particular item, it is much more of a method effect than a trait effect. So it's still loading pretty well over here, but it's really due to the scale it's on. And then these other two are good. And that's likely the pattern that you're going to see, where some items appear to be much better for traits and some items are better for methods. And I don't know that it means that you need to delete any particular item unless it doesn't load on the trait at all. That would be bad. But it is interesting to know, like, these items are much better at traits and these a couple of items are better at methods. But in general, for most of your items, you want them to be better for traits than methods. And so I always find it helpful if you kind of consistently, whenever you're diagramming these, not with sympaths because it will not be this pretty, or you're making tables to keep the traits on the left side, but that's just a personal preference, because the traits should be more important. So when I get over here, traits should be bigger than the methods, so greater than on the left. The other thing we can look at is correlations. So we're looking at those correlations for traits to traits and methods to methods. We've kind of tested this a little bit already, but especially if that Model 1 to Model 4 comparison was significant, this could tell you how bad that correlation is. So for both of these, it follows the same rules, discriminant validity, and we want our trait correlations to be kind of low. Now, not 0, because otherwise why are these traits on the same scale? So this is kind of going back to that EFA question of orthogonal versus oblique rotations. So I've always said, why do an orthogonal rotation? Because oblique rotations, if they're truly uncorrelated, will cover you. Also, in psychology, are there ever things that are uncorrelated? So I expect my traits to be correlated somewhat, but I don't want them to be super high. So I've kind of already tested that they're not at ceiling, right? So model 1 to perfectly correlated traits, which I think is model 3, tests if the traits are correlated at 1. Okay, hopefully that's not true. And this test allows you to make sure just sort of how different they are from 1. So we want them to be lower than 1, and we don't want them to overlap that much, knowing that they'll overlap some. In the methods table, this is a discriminant validity question as well, I want my methods correlations to be low. So we flipped that idea for methods, and we tested 1 to 4 if the correlation was 0. Now, often that test doesn't work. So here I can look at the numbers, the correlations, and say, well, hopefully it's at least below half, right? There is no, like I said, there's no hard and fast rule, but the lower the better, because that implies our methods are measuring very different pieces of our traits, which is good. Alright, so that is the end of that model. So it has 4 basic steps, 3 model comparisons, everything's compared to model 1, and then this parameter estimates piece is just sort of an additional way to look at. These 2 are correlation comparisons, and then these are loadings comparisons, so it just adds more information to those 3 steps, or the 4 steps with 3 comparisons. Alright, the other sort of flip side is to try a correlated uniqueness model. So in this particular type of model, instead of including methods latent variables, you just correlate their error terms. And so kind of, if I think about this, it makes a lot of sense, because we assume that we talked about this in CFA a little bit, we assume that the methods are correlated because they're on the same scale. So those questions or items have some little bit of correlation between their error terms just because they appear on the same page. And so this model allows us to just correlate those errors instead of creating a whole separate latent and correlating that. And then, like I said, this is completely separate from the Widaman steps. It's a different approach to MTMM, so we're going to try both. So what you do is you create a trait side of your model, which is the CFA that you've been doing before, and then instead of adding latents for your methods, you just correlate the errors within each method. So not across methods, within. And I'm really terrible at like drawing little covariance arrows, and so essentially what happens is you don't have those latents anymore, and so all 4 of these have t's, so I would correlate the errors between these 4 items, and then I would correlate the errors between these 4 items. Dave Kenny had a really great picture on his website, so this is a different model altogether, but this is more what it looks like. Here are traits, and then here are methods correlated within only their method together. So I've got my SUP method, SE here, and then SUB. And so they're not cross-correlated, so error 1 is not correlated to everything. It's only correlated to the errors that are on the same scale. And so you do get more estimates here sometimes, depending on the number of items, because of all of these correlations. So if you have a very big scale, this can get a little tedious, because you have to manually do those one at a time. In Lavon, anyway. So with this model, there's no real comparison. You just use those parameter comparisons explained a couple minutes ago. And people suggest using this model if model 1 for the traditional steps blows up in your face. This tends to work better because it figures out where that variance is going because it's correlated error terms. And so what you would do is you would check out the standardized estimates for each trait, and you really want them to be above 0.3, so this is kind of your traditional For for discriminant validity, you would check out the correlations for the traits and make sure they're not at ceiling, so we don't want them to be 1. And then you would check out the correlations for the error terms within each method to determine if they're highly correlated. So you want it actually to be 0. You would like the methods to not have super high correlations. So that item should be able to stand alone. So it's the same rules. For both of these, we want them to be low, assuming some reasonable amount of correlation between traits, and we would want the methods correlations to be low between errors, which would imply that you're not getting reactivity from question to question. Right. So altogether, there's 2 different paths that you can take for MTMM, sort of the traditional Widaman steps and this correlated uniqueness approach. And we'll try both in the example video and how to program these things and deal with explosions with a Haywood case.